Hello, welcome to all. In this episode, we'll be discussing about chemical equilibrium. Chemical equilibrium is something students learn from school classes itself. Higher secondary classes, they have especially gone through it. So the concepts are revised here. Then we go through what we call the thermodynamic and mathematical treatment of this chemical equilibrium also. So first we are going through, this is actually only a revision, the conceptual revision of what we have done in the school classes, higher secondary classes. That's it, chemical equilibrium. So chemical equilibrium can happen what we call in reversible reaction. What is a reversible reaction? A reaction which can occur in forward as well as reverse direction. That means products can react among themselves to give back reactants. That happens. Actually, any chemical reaction is a reversible one, theoretically. And even if a reaction appears to be completing, that means when equilibrium is established, we have predominantly products and reactants are negligible. That is it. And if you give suitable condition for reaction which seems to occur in one direction in a closed vessel and suitable conditions are given, we can see that all reactions become reversible in some respect. That is it. That we have to take into account, because at the microscopic level or the molecular level, the process can occur in both directions. That is it. We take the decomposition of dinitrogen tetroxide, that is a dimer of nitrogen dioxide, NO2. So if you take N2O4 in a closed vessel and give sufficient temperature, keep at the temperature. Initially increase temperature to particular level and keep it at that temperature. Then we can see that after some time equilibrium is established. Initially there is only decomposition of N2O4. Its rate comes down as amount of N2O4 decreases. But what happens to the reverse reaction? It picks up as more and more NO2 is formed. And at a particular point, both the rate becomes equal, equilibrium is established. That is it. So we can see that it is dynamic in some way. The process can be occurring at the microscopic level, but we do not notice it at the macroscopic level. That is it. If you take the concentration of the reactants and product, the curve will be somewhat like this. So N2O4 decreases and attains a particular value and remains constant. That is true for NO2 also. Double arrow indicates equilibrium and reversible reactions. Equilibrium constant. It's simply the classical definition that we see in the lower classes is that the ratio of product of active mass or molar concentration of the reactants to that of the of products to that of the reactants. That is it. And that we can obtain from what you call law of mass action. That is the classical derivation of equilibrium constant. But we have more rigorous thermodynamic methods as well. This is the classical method. So we have the forward reaction and reverse reaction or backward reaction. The rate is proportional to product of active mass of the reactants. That is the active mass or molar concentration. For practical purpose, active mass can be taken as equal to molar concentration. That is it. So here forward reaction, decomposition. So rate constant of forward reaction into concentration of N2O4. For the reverse reaction or backward reaction, rate constant of that reaction into NO2 square we have to take. NO2 square, concentration of N, because 2 moles of NO2 are involved. We consider as 2 reacting species, 2 molecules of NO2. And at equilibrium, this becomes equal. When they are equal, what happens? We can equate it and you can take Kf by Kb. That will be equal to NO2 square divided by N2O4. Products divided by reactants. Concentration of products divided by that of reactants. So that is our equilibrium constant. Right? That is a constant. It does not depend on initial concentration. It depends on temperature alone, equilibrium constant. That is a peculiarity of equilibrium constant. If we have a general reaction like this, A moles of A plus B moles of B gives C moles of C plus D moles of D, then equilibrium constant Kc will be C raised to C into D raised to D divided by A raised to A into B raised to B. You have already seen it. We can take these equations and write the equilibrium constants Kc. Okay, equilibrium can be reached from either direction. That is a peculiarity. You can start with N2O4, or you can start with NO2 alone, or you can start with any mixture of N2O4 and NO2. You will get an equilibrium where the ratio is the same. Which ratio? N2O4 square divided by, NO2 square divided by N2O4. Concentration of NO2 square divided by concentration of N2O4. That is the equilibrium constant. That should be the same. Whatever may be the initial concentration, once equilibrium is reached, the ratio has to be kept constant. Okay, it can be attained from either direction. Graph will somewhat look like this. And now we take the concentration. In the case of formation of ammonia, we start with the nitrogen and hydrogen alone. Then the concentration graph will be as in the first figure. Nitrogen and hydrogen decreases and attains a particular value, remains constant. Ammonia, initially there is no ammonia, it increases and attains a particular value, remains constant. The second one is the reverse. We start with ammonia. Then the concentration of ammonia decreases, attains a particular value. Nitrogen and hydrogen, the opposite. Right? Equilibrium constant will be the same. No difference from which direction you start. Or you can start with a mixture containing all these three in any desired, arbitrary ratio. But once equilibrium is attained, that ratio will be, Kc will be the same. The significance of K. K is very large, greater than 1, far greater than 1. Then that means products is favored. When equilibrium is established, we have predominantly products. If K is very less than 1, what does it indicate? When equilibrium is attained, we have predominantly reactants. Only very small amount of products will be present. Right? The extreme case of this, when we have what we call very high value of K, we say the reaction is complete. It happens in one direction. The amount of product reactant will be negligible. If the reverse is true, we say that the reaction does not take place. Right? That is it. Equilibrium constant, you can manipulate it in the case of chemical reactions. You can consider this decomposition of N2O4 as well as dimerization of NO2. We are approaching the reaction in actual reaction condition. You can start from anywhere, it doesn't matter. But if you are considering the reaction as decomposition of N2O4, you have the equilibrium constant as we have seen. And if we approach it as dimerization of NO2, then the equilibrium constant will be reciprocal of the other. So if you reverse the representation of a reaction, equilibrium constant, what we have to do, you have to take the reciprocal. That is it. Now there is another case. We have two equations, two reactions that takes place at an elevated temperature. Decomposition of carbon dioxide to carbon monoxide and oxygen, and decomposition of water into hydrogen and oxygen. That's fine. Then we are given another reaction taking place under the same condition, and we are asked to give the equilibrium constant under the same temperature. Right? CO2 plus H2 gives CO and H2. You manipulate these two equations to obtain the third equation. And what happens to equilibrium constant in that case? That is of our importance. You can see that carbon dioxide 2 moles are involved in the first reaction. So divide the first equation by 2. Then what do you do with K1? In such a case, if you divide an equation by a number, say n, you take nth root. Here you take square root. So when you divide it by 2, the equilibrium constant will be square root of K1. That is it. Now we have the second equation, decomposition of water. Water in the final reaction, we require water in the product side and oxygen, hydrogen in the reactant side. So you reverse the reaction. Right? When you reverse the second reaction, equilibrium constant will be 1 by K2. Then you can see that only 1 mole of water is required. So you divide that reversed equation by 2 again. Then you have to take the square root. So it will be 1 by square root of K2. Now you add these two equations together after these manipulations. Then what do we have to do? When you add two equations together, you multiply the equilibrium constants. So it will be square root of K1 into 1 by square root of K2. I am not showing the steps. You do yourself. Right? then it will be clear. Using these instructions, oral instructions, you do it. Then it will be very clear for you. So the principle can be summarized like this. If you multiply an equation by a number, you have to take that power. So if you multiply by n, you take the nth power of the equilibrium constant. If you divide an equation by a number n, you take the nth root of the equilibrium constant. And if you add two equations together, you multiply the equilibrium constants. Right? And if you reverse a reaction, then you take the reciprocal. That is it. Using these concepts, you can do manipulation to any set of equations. That is it. Now, equilibrium constant can be expressed in terms of other parameters like partial pressure. So it will be like that. Partial pressure of C raised to C into that of D raised to D divided by that of A raised to A into that of B raised to B. That is it. Equilibrium constant in terms of partial pressure. That is applicable for gaseous reactions. And you can have a relation between Kp and Kc for a reaction. It will be Kp is equal to Kc into RT raised to delta n. Because we know in the expression for Kp, partial pressure, we can replace that by, we know P is equal to N by V into RT, or P is equal to molar concentration into RT. So we can substitute for partial pressure as molar concentration into RT, and you do the mathematical manipulation, you get this equation. Where what is delta n? Number of moles of the products minus number of moles of the reactants in the balanced equation. The stoichiometric coefficients, you take the difference. That is it. Right? It can be negative or positive or 0, delta n. Always a whole number. That is it. Then we can have equilibrium constant in terms of mole fraction. So you can have this type of expression. Mole fraction is represented as x. So x of C raised to C, x of D raised to D, the product divided by x of A raised to A into x of B raised to B. And we know partial pressure is equal to mole fraction into total pressure, and we substitute into the expression for Kp, what we get, Kp is equal to Kx into P raised to delta n, where P is the total pressure. Right. Now you can have an equilibrium constant in terms of simply amount of substance or number of moles at equilibrium. So that is it. Number of moles of the products multiplied divided by number of moles of the reactants. So we can also show that this Kc is equal to Kn into V raised to minus delta n. Minus delta n. Here it is. V is the total volume, if that remains constant, of course. The Châtelier principle that you have studied in lower classes. So you are disturbing a system in equilibrium by applying a constraint. It can be change in temperature, pressure, or change in concentration. Right? If you change the concentration of reactant or product, what will happen? The system will try to adjust it, try to reduce that effect. Temperature also. What the system will do? Reduce the effect. Temperature increasing means supplying heat. So the reaction will move in the direction in which heat is absorbed. Right? What does it mean? Exothermic reactions are favored by low temperature and endothermic reactions are favored by high temperature. Pressure. If you increase pressure, system will try to reduce that effect. So how it can be reduced? By decreasing number of moles. So if reaction will shift in the direction when pressure is increased, where number of moles comes down, so that effect is reduced. That is it. We take the example of Haber process, manufacture of ammonia, and explain it. 1 mole of nitrogen and 3 moles of hydrogen give us 2 moles of ammonia. Right? Here, if you increase nitrogen on hydrogen, already equilibrium is established, you pump in nitrogen on hydrogen again to the reaction mixer, more of ammonia will be produced. Right? You can remove ammonia from the reaction mixer because ammonia is easily liquefiable. You can liquefy it and remove. Then the reaction mixture can again undergo reaction. That is done in Haber process as well. You remove ammonia and it is again recycled with more of nitrogen and hydrogen. Then what will happen? More of ammonia will be produced. And the cycle is repeated over and over again. That's it. Then if we can have what you call effective temperature. What happens when temperature is increased? This is an exothermic reaction. Which one? Formation of ammonia is an exothermic reaction. So if you supply heat, the reaction will shift in which heat is absorbed, that is backward. So high temperature favors backward reaction or low temperature favors forward reaction. So more amount of ammonia can be produced at at lower temperature. At high temperature we will get less and less amount of ammonia. But in the actual manufacture you will be using a temperature near about 700 Kelvin. Why we use high temperature? Because approach to equilibrium, this is the chemical equilibrium and this is actually thermodynamics, principle of thermodynamics as well. But the time to reach equilibrium, approach of equilibrium is controlled by chemical kinetics where temperature plays a role. Temperature increases rate, that we know. So equilibrium will be approached within a shorter period of time at a higher and higher temperature. So we use an optimum temperature, that is 700 Kelvin in this case. We get small amount of product only, but that is obtained within a short period of time. Theoretically, if you use a very low temperature, we can get more amount of ammonia, but it will take a too long time. That is not practical. That is the reason, right? Then we can come to the effective pressure. Here we can see that we have 4 moles of reactant giving us 2 moles of products. So if you increase pressure, what will happen? Number of moles decrease. In which direction it can decrease? More amount of product can be formed. That is it. Heterogeneous equilibrium, where solid and gases are involved, or liquid and gases are involved, or solid and liquids are involved, we call them as heterogeneous equilibria. You consider decomposition of silver carbonate. You can have calcium carbonate decomposition as well. Equilibrium can be established only when you do the reaction in a closed vessel. If it is an open vessel, carbon dioxide will escape and normally it is difficult to obtain equilibrium. Right, here we can obtain equilibrium like this. Then equilibrium constant, it will be concentration of Ag2O CO2 divided by concentration of Ag2 CO3. Concentration of solids in heterogeneous reactions are taken as a constant. Right, the reasons we do not go into now. So they are constant, then equilibrium constant will be simply concentration of CO2 alone, X by V we put, or in terms of partial pressure it will be partial pressure of CO2, the equilibrium constant. That's all. Okay, that's for the day, and we can have what we call unit for equilibrium constant. Kc will have unit and it will have the units of molar concentration. That is it. We are using molar concentration to raise to some power. It will be raised to the power of delta n. That will be it. Kc. And Kp also will have unit. Here that will be unit of pressure raised to delta n. That will be the right. Similarly, mole fraction will have unit in terms of mole fraction. Mole fraction is a fraction only. It has no unit. So Kx will not have unit. That is it. Okay, fine. But Kn will have unit. Number of moles is a unit, amount of substance, and it will be moles raised to delta n will be the unit there. Then we have what you call a thermodynamic equilibrium constant, where we take what you the term called activity. That I haven't mentioned in the slides, but you can simply memorize it. So instead of this molar concentration, partial pressure, mole fraction, we put the term activity. Then you get what you call thermodynamic equilibrium constant, and that will have no unit. Activity is considered to have as a dimensionless quantity. That's why. Okay, then we have to consider the temperature dependence of equilibrium constant. That will be doing in the next episode. But we have to be sure that the equilibrium constant Kc and Kp does not depend on pressure or concentration, initial concentration. It depends on temperature. It changes with the temperature, both Kp and Kc. But Kx will depend on pressure as well. It will change with pressure. and Kn will change with pressure as well as concentration. That you memorize. The reasons we are not entering now, just now. Okay, thank you. We'll see in the next episode. Bye.